Hi, I'm Guin Gilman from Worcester Polytechnic Institute, and today I'm going to be talking about the scheduling policies of the thread block scheduler on NVIDIA GPUs and how they impact the performance of concurrently executed kernels. Concurrent kernel execution is the process of executing two independent GPU kernels at the same time on the same device. It has been proposed as a means to improve the utilization of general-purpose GPUs, but to accomplish that, the scheduler has to efficiently divide the GPU's limited resources among the kernels. However, characterizing the performance of the scheduler is difficult due to the black box nature of NVIDIA devices. To do so, we used empirical observations of real hardware and inferred the policies of the thread block scheduler on the Pascal, Volta, and Turing GPU microarchitectures. As an overview of our findings, we saw that even though most literature assumes that the scheduler uses a simple round-robin policy, it actually chooses where to assign a thread block based on the local resource availability of the streaming multiprocessors. We call this the most room policy. We also examined the performance implications of the most room policy under concurrent workloads and found that the policy can result in counterintuitive performance drops with only small changes made to the structure of the concurrent kernels. Additionally, the performance of a kernel in a concurrent workload is challenging to predict because it depends on factors that are external to the kernel itself, such as the scheduling policies of the thread block scheduler and resource contention. To put these findings into context, we first need to give a high-level overview of the terminology and workflow of the CUDA programming model on NVIDIA GPUs. So here's a diagram of that workflow. The code executed by the GPU is known as a kernel. Kernels consist of independent groups of threads, known as thread blocks, which execute in parallel. The code of each block is identical, but each block operates on a different subset of data. These thread blocks make up a logical array called a grid, and both blocks and grids can be defined in up to 3 dimensions. The GPU executes a kernel by scheduling the thread blocks to hardware units of computation known as streaming multiprocessors, or SMs. SMs have a fixed set of resources and resource limits, such as threads, shared memory, and registers. During execution, blocks are scheduled under the constraint that the total resource requirements of the resident blocks on the SM cannot exceed any one of the SM's resources. So the thread block scheduler has to be aware of the remaining resources on each SM. Thus, in order to examine the performance of individual kernels in concurrent workloads, and to analyze the overall performance in terms of GPU resource utilization, it is important to understand the way computational resources are assigned to the kernels, and this means understanding the thread block scheduler. Deriving the policies of the thread block scheduler involves answering 3 key questions. First, when does the scheduler choose to schedule another block? Second, which block is chosen to be scheduled next out of all the kernels on different streams with unscheduled blocks? And finally, where will the chosen block be placed? In other words, which SM is chosen? The answers to the first 2 questions are explained by a widely observed scheduling policy called the leftover policy. Blocks are always scheduled to an SM as soon as there is enough space, meaning that there are enough of all the resources needed by the block available on that SM. The key aspect of the leftover policy for concurrent workloads is that all of the blocks of the earliest launched kernel have to be scheduled to an SM before any of the blocks of the other kernels can be scheduled. This is true even if there's enough space for blocks of the second kernel, but not of the first, as we can see from this simple example. Here, we see that there is enough space to schedule a block of kernel A to each SM, so 5 of them are placed onto the SMs. However, when placing the 6th block, there is not enough space, and since these thread blocks require the same amount of resources, we can't schedule any more blocks from kernel A. We might then look at kernel B, and there is enough room for blocks from kernel B, but there are still blocks of kernel A ahead of it in the execution queue that can't be scheduled yet. Kernel B has to wait for all 5 of those kernel A blocks to be scheduled first, according to the leftover policy. However, this does not answer the question of which SM the selected block will be placed on. This is where the most room policy comes in. While it has been previously assumed that the scheduler chooses SMs based on a round-robin policy, our results indicate that a kernel block will be scheduled to the SM that, at the time of the scheduling, can support the most blocks from the current kernel. Blocks require a number of computational resources which the SM provides, and if it requires more of any one of those resources than an SM has available, it cannot be assigned to that SM. Thus, the first resource to run out when assigning blocks of that kernel to SMs becomes the limiting resource. When there is a tie, the scheduler appears to use a per-device fixed ordering to break the ties between SMs, always picking the first SM that appears in that ordering. Let's look at a demonstrative experiment on the Pascal GPU as an example. We launch kernel A with 5 thread blocks, one for each SM, although we only picture the first 2 SMs here. Each block of A uses half of the limiting resource on an SM, and they each run for a different amount of time. So block A0 is assigned to SM0 by the scheduler, and it finishes executing first, while A1 is assigned to SM1 and finishes executing next, and so on. Kernel B is composed of 3 blocks, each using 2/5 of an SM's limiting resource. B is launched at exactly the time when only A0 has finished executing. So SM0 is empty, but the other 4 SMs each have 1 block of kernel A still executing on them. If the scheduler followed a pure round-robin policy, as is widely believed to be the case, then we would expect that blocks B0, B1, and B2 would be placed on SM0, SM1, and SM2 respectively. Instead, the scheduler places 2 blocks on SM0 and 1 block on SM1, which can be explained by the most room policy. Let's start with B0. When B0 was scheduled, SM0 was empty and thus had room for up to 2 blocks of kernel B, which each take 2/5 of the limiting resource. The other 4 SMs, having 1 block of kernel A already resident and using half the limiting resource, only had room for 1 block of kernel B each, so it was placed on SM0. The second block of kernel B was also scheduled to SM0. With B0 already executing, SM0 had 3/5 of the limiting resource available and could then fit only 1 block of kernel B. As all of the SMs could fit 1 block of kernel B, the first SM was chosen per the tie-breaking ordering. Finally, the third block of kernel B was scheduled to SM1. At the time of the decision, SM0 was executing 2 blocks of kernel B and thus could fit no more blocks of B. So, the scheduler chose the first SM out of the remaining 4 that could fit 1 block each, which was SM1. This behavior, where the scheduler places the next block onto the SM which can host the largest number of blocks of the current kernel, is what we term the most room policy. So the next question to answer is how the scheduling policy impacts the performance of concurrent kernel workloads. Our results show how it can cause large and counterintuitive variations in performance when only a small change is made to the kernel structure. Also, the performance of individual kernels is difficult to predict because of its dependence on factors external to the kernel itself. Now I'll describe the experiment we designed to examine concurrent kernel performance, this time on the Turing GPU, which had 68 SMs. Kernel X had 67 blocks of 512 threads, and it was launched first, guaranteeing that all 67 blocks would be scheduled to a separate SM, with the last SM left empty. Kernel Y had 2 versions, one with 8 blocks of 32 threads, and one with 8 blocks of 33 threads. The version with 33 threads was the concurrent isolated case, pictured here on the right. The limiting resource for kernel Y was the number of threads, and so all of the 8 blocks of kernel Y were scheduled to the empty SM67. While the 2 kernels were executing at the same time, none of their blocks shared an SM. The version with 32 threads was the concurrent colocated case, pictured here on the left. Here, the limiting resource for kernel Y was the maximum number of blocks allowed per SM, and so the first of kernel Y's blocks was placed onto the empty SM67, but the rest were placed according to the tie-breaking ordering with 1 per SM. This resulted in 1 block of kernel Y and 1 block of kernel X on 7 of the SMs. The collocation of these 7 blocks are the only differences between the 2 kernels aside from having 1 less thread. Finally, we ran the 2 applications serially as well as a base case to compare the concurrent performance to. We examined the execution times of 4 common types of kernels in these 3 cases. The first was L1 cache-dependent kernels. As all blocks on the SM share the same L1 cache, the performance of these kernels depends primarily on the amount of cache contention, so they perform better when the cache is available for their exclusive use. The next was compute-intensive kernels. These are kernels that perform a very high number of computational operations, and their performance is bounded by the number of these operations that can be performed on an SM per unit of time. Another type was memory-intensive kernels, and these depend on global memory throughput for their performance due to the high volume of global memory accesses that they incur. Finally, we looked at PCIe transfer bandwidth-dependent kernels. For a system with a discrete GPU, the PCIe link connects the CPU and GPU. All input data and code must be transferred over this link. However, for NVIDIA GPUs, a feature called Unified Virtual Memory allows data to be fetched asynchronously as the kernels are being executed using paging. PCIe bandwidth-dependent kernels are ones whose performance depends on the speed at which page faults can be handled by the GPU. From these results, we can see that the impact of the most room policy on performance depends on the type of kernel being executed. For example, the scheduler's decisions disproportionately affect individual kernel performance for compute and memory-intensive kernels, resulting in poor kernel-level fairness. Transfer bandwidth-dependent and L1 cache-dependent kernels are impacted by contention for resources such as PCIe bandwidth, the TLB, and the L1 cache, which is worsened when the two concurrent kernels are co-located. We can also see that when the blocks of kernels X and Y are executed on separate SMs, concurrency offered an improvement in total execution time when compared to serial execution. However, when blocks from different kernels were placed on the same SM, that improvement lessened, and in some cases, dissipated entirely. This demonstrates a key fact. External factors such as resource contention and the decisions of the thread block scheduler all impact the performance of individual kernels when run concurrently, making their runtime extremely difficult to predict. In summary, we have shown evidence that the thread block scheduler on NVIDIA devices uses a most room policy to assign thread blocks to SMs, and that this policy and other external factors can drastically impact the performance of kernels in concurrent workloads. We hope to expand on this work in the future by using it to inform the creation of more robust concurrent scheduling policies, which take into account factors such as potential resource contention when placing thread blocks onto SMs.